Yeah, hello, my name is Jens Dietrich. I'm Associate Professor at Victoria University of Wellington in New Zealand, and today I would like to talk about DALEQ, an open source tool we have developed and recently released to aid engineers working in software supply chain security, in particular for the Java platform. So DALEQ is open source. You can access it here from this GitHub project, and there's a command here to clone the repository. It's written in Java and uses a Maven build system, so once you have downloaded this, you can run Maven to build it. I've already done this here, so I opened it in an IDE that supports the Maven format. That's actually IntelliJ, but any other tool or command line will work as well. So to build this, you basically use mvn package. I use this additional parameter here to skip the test, simply to make it a little bit faster for the sake of this demonstration. So let's quickly do this. So it compiles the sources and packages it all up in a single executable that also contains all dependencies, and you can find this here in this target folder. So once you have done this, you can basically start using it. And I think I have a command somewhere here in the history. And I don't really want to run this to the end. It takes a few minutes, it's actually quite fast. But I just want to discuss the parameters you need to provide to run DALEQ. So the first parameter here is this souffle parameter, and that really points to the souffle executable. So DALEQ uses Datalog, like many other state-of-the-art static analysis, CodeQL for instance, and that's really a reference to the Datalog executable. So the Datalog engine that's being used here is souffle, which have to be downloaded and installed separately. DALEQ can also locate this in the path, but you can also explicitly, as I do it here, pass set -d souffle parameter to set this. The basic parameters you have to supply are then a reference to the executable, that is the file we just built. That's the DALEQ executable. And then basically you pass with those two parameters, J1 and J2, to jar files. Jar files are Java binaries, so that is basically what the Java compiler produces, or it's actually a zip file around the files the Java compiler produces. So that is how Java binaries are being published in repositories such as Maven Central. And the supply chain use case is that a developer, for instance, publishes one of those jar files in Maven Central built from the source code of some open source project. And now another organization is really concerned about the security of the build. So it tries to reproduce the build or run an alternative build, creates another jar file from the same source code. And now you have two jar files, and now it happens to be the case that often those jar files are not the same. So the question is whether the differences you observe are security critical or can be explained by, let's say, different compilation patterns. And that's exactly where DALEQ helps you to make this assessment. You can see there are three more parameters. Let's quickly talk about those. So you can optionally also supply the sources. The sources are also wrapped up in jar files, which are basically just zip files. And the idea here is the following. When you publish a binary, such as is the case here, so that's a reference to such a binary, let's say on Maven Central, then typically you are being asked, or it's custom, to publish the sources that binary was built from alongside. So if you have the sources, you can basically test the assumption that those two binaries you are comparing have been built from the same sources. And that comparison itself yields some really interesting insights, as we will see in a minute, where I talk about some examples. And DALEQ basically supports the source code analysis as well, so that really explains those two additional arguments we pass. The final argument is just a folder where the report is being created. So DALEQ conceptually takes those files, compares them, does some analysis, creates an HTML report. That is where the HTML report goes. So let's have a look at some of those reports. So we start here. I've already prepared this now. You might actually wonder at this stage about the runtime, how long it would take DALEQ to analyze a typical Java project with two alternative jars. And It usually takes a few minutes for smaller programs, like 1, 2, 3 minutes. For larger programs, in our experience, it can take up to half an hour. So the particular binary we are interested in here is GTA, so that's some transaction monitor. So you can actually see a reference here which encodes the name of that artifact within a group. So Maven artifacts actually have structured names, so there's a namespace called the group ID and then a local artifact ID followed by a version. So that has all this information. So there's actually a reference to a local path here. That's what we passed to the tool as an argument. But that basically encodes that I had earlier downloaded the respective jar file from Maven Central. So the first jar file is what the developer has built and released on Maven Central. The second jar file is obtained from a different source. In this case, that is actually Google. Google has a project called Google Assured Open Source Software, where they try to independently rebuild open source packages, including Java packages, and then compare them with the original artifacts in order to assess whether the builds have been compromised or not. And other organizations do similar things. A good example for this is Oracle Build from Source. And as a disclaimer here, that project has also been sponsored by Oracle. And there's a collaboration with Oracle researchers that related to this tool. Okay, so let's have a look into this report that has been generated by DALEQ. So first, everything is presented as a big table, and the rows in this table correspond to the resources within the respective jar files that are being compared. So the first thing we do here is in the second column, so each column corresponds to a particular analysis. The second column analyzes whether respective resources are present in either file. And you would typically expect this, but interestingly, that is sometimes not the case. And in this particular example here, we see that that particular check fails for 2 resources. Let's have a look at the first one. So meta info in Java jar files contains metadata, basically. So there's a subfolder Maven, and then somewhere down there is a file called pom.properties. If you click on this little delta symbol, delta stands for diff, you can see that there's a resource that is present in one jar. So the first jar is the one produced by Google Assured Open Source Software, but it wasn't present in the jar file built and released on Maven Central by the developer. So that's interesting. So I don't think that's security relevant in this particular case, but that's exactly the kind of analysis a security engineer wants to perform. Yeah? So some builds maybe maintain additional metadata used during the build and package them into the jar file, but that's of course enough to make those resulting jar files to be different, to different jar cryptographic hash codes, for instance. So the next assumption we test is whether the same source code has been used for those 2 builds, because that's very much the claim, that we start with the same sources, build 2 different jars in different settings in different environments, and then we compare them, and hopefully that gives us some insights about the security of the build processes being used. So interestingly, in this particular case, those checks fail as well, and we see this in column 3, which character by character compares the source code associated with the respective binaries. And when I say associated with the respective binaries in the original jars, of course we have .class files, that's bytecode, but because we can also pass the associated source code to the analysis, we can, in the source code jars, locate the source code which is associated with this particular bytecode here, and then we can compare this between the 2 jars being analyzed. So that fails. If you click here on this little delta again, you see some additional information that explains why it fails. So that's basically just a diff. That's fairly straightforward usually to explain why things are different. And we can see here that there are some differences which are all related to legal comments. So Google during the rebuild process, somehow inserted additional legal comments, and that basically shows up in this comparison. So the next column, which is column 4 here, does some additional source code analysis. Now we are looking for equivalence. So the way DALEQ goes about this is, again, very straightforward. So instead of comparing two source code files character by character, what we do instead is we build abstract syntax trees and compare those trees, and that allows us to look for two particular patterns or to ignore two particular sources of non-equality. First, that is different comments, so we just ignore comment nodes. The second thing is, as we compare trees, and there are certain formatting differences like new line separators, which might differ across the sources, which we can just ignore. So, and with this check now, we see that all sources are equivalent. The next check in column 4 is that we basically just compare the files bit by bit, and again, that confirms some of the observations we made earlier, that the source code files, for instance, here are different, and the class files are actually different as well. That also applies to some metadata, so we can actually see here that the license files are different. Again, let's have a quick look at this delta. It's mainly formatting and some additional legal comments in here, so that is consistent with what we observed in the when we had a look at the source code differences. And yeah, maybe for another example, let's have a look at some metadata here. So there's this meta-inf manifest file, which is the metadata in jar format. And again, we see some differences here, some additional headers or properties being inserted into one of the metadata file, which is not available in the other version. Okay, so the main purpose of the tool is actually to compare bytecode. So we haven't actually done this yet, but we do this in the last 3 columns. And the way that works is that we transform bytecode into some text format, and then we diff the text. And so we first use the standard Java disassembler for this purpose, which is a program that is part of the OpenJDK distribution. It's called Java P. And you run this with 2 different parameters. The first is -v, which is verbose. So that is a very detailed representation of bytecode in text format. And we then can, again, compare the output of Java P on the respective binaries. And so let's do this here. So let's maybe have a look at that particular class called heuristic commit exception. And if we do this here, then we can see that the checksum is different. And maybe let's just talk about this one example here where things are different. So there's a header on bytecode files which encodes bytecode versions that's set during compilation. And it turns out that that is different. So there was a slightly different compiler being used, and the output bytecode version was set to different values. It's maybe something else interesting we can just have a quick look at. So I mentioned earlier that Java P-V is very detailed in the output it produces, and it also contains the line number table, so you can see that there are differences in line numbers. And that is likely to be related to the difference in source code we saw earlier. You might remember that the Google build inserted a lot of legal comment at the top at the source code files, so that of course changes also line numbers, and that causes the bytecode to be different. So we, however, often find that if we just have a look at the comparison of the output of Java P-C-P, which is a much more compact format, then with the exception of one particular file, the output is the same. And we can interpret this as, if we ignore during the comparison a certain amount of noise like the line number tables, then there are good reasons to consider the bytecode as being equivalent. So there's, however, one particular class where that is not the case, and we have a quick look at this now. So you can see here that there are certain differences when it comes to those invoke special instructions, and they have an argument here, and that is a reference to the constant pool. So it is widely known that if you compile with slightly different compilers, the ordering of the constant pool is typically different. That's again widely considered to be noise. And DALEQ actually realizes this and basically parses this. So I don't really want to go into those details here. That's related to the explanation of the DALEQ results. I will do this in a separate video, which will be part 2 following up from what we discussed today. But what I do want to do is I want to show you another example here where we have a different project. Now we are comparing a build released on Maven Central. You can actually see this here in the parse name, with a build that has been performed independently by Oracle's build from source project. Now we see that we have a lot of parses here, so the bytecode is almost identical, but still there are a few differences where even that very strong Java P-P based analysis tells us that there are significant differences, and I just want to have a quick look at this here, what the differences are here. So sometimes there are bytecode instructions in the one jar file, like that invoke interface, that are significantly different, the different instructions being used in the other format. And that is again something DALEQ can still establish as being equivalent. So if you have a look at the at the source code repository, there's references here to some papers, and in particular if you have a look at the first paper that's being listed here, that has an evaluation on how effective DALEQ is in practice. And maybe going back to the slide, so you might really wonder how many of the pairs of those classes that are being compared, which are flagged as different by state-of-the-art tools, like by the Java disassembler, and in the experiments we report in this paper, we also used another tool called JNorm. How many of those can be reported as still being equivalent by DALEQ? And the answer is between 80 and 90%, so DALEQ is very effective in what it does, and a significant improvement over the state-of-the-art. One of the advantages DALEQ has is the generation of provenance data that sits behind those little links here, and I will talk about this in a second video. Thank you for your attention, and if you have questions, please feel free to email me or to open issues on the DALEQ project. Thank you.